In part 3, I tried to explain the reactions that occurred during the separation of each group and discussed the flowchart. That is, the procedure used for the separation of the 7 groups, resulting in 6 test tubes. That is, if all groups were contained in a hypothetical ore sample. The Group 2 test tube would contain both subgroups, 2A and 2B, which will be discussed in this presentation. I will also try and describe the chemical reactions that take place for the separation of analyte, that is, the element of interest, within each group, so that the average prospector, miner, or hobbyist, without a chemistry background, will be able to understand the principles involved and how to identify, that is, to determine and confirm the presence of an element within your samples. I am Rob Boyko, Boyko Mineral Exploration, and welcome back. At this point in time, I need to discuss some basic concepts regarding compound formations of metal complexes, that is, basic ionic bonding of atoms and ions. The periodic table shows the elements as well as their atomic weights and their ionic electrical charges, such as plus, minus, +2, -2, etc. When these atoms come together, the compound's electrochemical charge must be equal to 0. The charges are then said to be balanced. For example, as unlike charges attract similar to magnets, coming together, atoms will do the same. Each metallic element will have a different ionic charge. Some will have only a single charge. The table shows the charges vertically at the top right corner of each element in the table. Copper has 2 charges shown, but there are actually more. Ferric iron has a +3 charge, the first charge listed. The first listed charge is the most common charge of the atom. However, ferrous iron has a +2 charge. Each of these elements are also named as iron 3 and iron 2, which denotes the charge of the iron atom. For lead to become lead chloride, lead has a +2 charge. Now it will combine with the nonmetallic chlorine atom to produce lead chloride. However, it takes 2 chlorine atoms to combine with the lead atom, as chlorine has a single listed -1 charge. The single minus refers to the charge as -1, same as a single positive sign, which means +1. The basic formations between atoms and compounds, that is molecules, can be either single displacement, double displacement, dissociation, better known as decomposition, or combustion, which is temperature related. There is also synthesis. I just want to focus on 3 of these processes without a lot of detail. For a synthesis to occur, 2 atoms or an atom and a polyatomic ion must bond. A polyatomic ion is basically a pair of nonmetal atoms bonding together by electron pairing, that is, orbital sharing, commonly known as covalent bonding. Some atoms must form molecules in this way, but as pairs. These molecules are referred to as diatomic molecules. These are hydrogen, oxygen, iodine, chlorine, fluorine, bromine, and nitrogen, and most are gases. This equation shows a synthesized reaction of the silver atom and a nitrate ion, bonding to form silver nitrate. Note the ionic charges. Polyatomic ions are or can be similar to a single atom. They do not dissociate easily due to their covalent bonds. These bonds are considered to be the strongest type of atomic bonding, which is beyond the scope of this presentation. Silver nitrate, the nitrate being the polyatomic ion, is usually shown without parentheses unless there is more than 1 ion in the formula. These will dissociate and recombine with a hydrochloric acid, which is dissociated in the liquid water to form silver chloride and nitric acid. The nitrate molecule has a -1 charge, or the total ionic charge of -1. The silver atom also has a +1 charge. The charges are shown in the reaction equation. This is a double displacement reaction. A single replacement reaction is simply a pure metal such as silver scrapings from a silver ingot which is dissolved in hydrochloric acid, which produces the silver chloride precipitate. Water in these reactions is usually not shown, as water is a liquid containing ions. Ions are the reacting agents. The dissociation, that is decomposition reaction, is simply the material dissolving into the respective ions or atoms in solution. The test tube that contains a precipitate that was labeled Group 1 or just 1 will contain compounds that are precipitates of the elements of silver, lead, and mercury. This precipitate should be all white in color. The acid used at the beginning of the group separation was hydrochloric acid. Its decomposition is hydrogen ions and chlorine ions all floating around in water. How an acid dissolves materials is beyond the scope of this series, but it is enough to state that acids, solvents, and others will dissolve materials. The chlorine in the water makes the solution a chloride solution. The solubility and water table shows the elements in group 1 category are all insoluble in a chloride solution and will not dissolve. They would remain as a residue or, in some cases, a precipitate. A classic example is silver nitrate solution. Add enough hydrochloric acid and a precipitate containing silver in the form of silver chloride will appear as a solid. If sodium chloride was added to the solution instead, it would have the same effect, as the chloride ions bond with the silver ions in the solution. The formation of precipitates and the dissolution of a compound is also determined by their KSP value. As discussed earlier, the larger the solubility product constant is, the more soluble is the compound. As shown, the solubility constant, KSP for lead 2 chloride, is quite high compared to the remaining and will dissolve in hot water. The remaining chloride will remain as a residue. For the conformation of these 3 chlorides, for the lead, potassium iodine is added. The reaction is lead chloride plus potassium iodine will give us a lead iodide solid, plus potassium chloride ions in solution. For the silver, ammonium hydroxide is added along with nitric acid, giving us 2 reactions in sequence. The first being the silver chloride and ammonium hydroxide, giving us a silver ammonia chloride complex plus water. The second reaction is the silver ammonia chloride plus nitric acid gives us ammonium nitrate and the silver chloride solid. For the mercury, the reaction will be the mercury chloride plus the ammonium hydroxide will give us mercury, elemental mercury, plus mercuric amido chloride, ammonium chloride, and water. The mercurous complex will partially decompose into a finely divided liquid mercury, which presents itself as a black color as a conformation for mercury. For the group 1 separation, to the test tube number 1, add 5 drops of cold distilled water to remove any soluble contaminants. Carefully decant and discard that water. To the residue, add enough distilled water to equal the volume of the precipitate. It should be a 1-to-1 ratio. Heat the water in a water bath to about 80 degrees centigrade while gently stirring with a glass rod. Centrifuge and decant into a clean test tube. Do not discard the residue or the filtrate. From the liquid, which is commonly referred to as the filtrate, place 1 drop of this liquid onto a glass slide or watch glass. Add 1 drop of potassium iodine. If a yellow precipitate forms, it confirms the presence of lead. To the residue, add a few drops of ammonium hydroxide. It should be 50% weight to weight. Centrifuge and decant into another clean test tube. From the liquid part, Take one drop and place it onto a clean watch glass or glass slide and add a few drops of diluted nitric acid. Any white precipitate that forms will confirm the presence of silver. The precipitate or residue that remained after the addition of the ammonium hydroxide, if it's black in color, it confirms the presence of mercury. Any other color is considered to be an error. The test tube number 2, which contains the group 2 sulfides, has to be split, that is separated into two groups, 2A and 2B. This is accomplished by adding ammonium polysulfide. The precipitate colors are shown. The polysulfide reacts with the metal sulfide to create thiosalts, which are soluble while the others remain in solution. This is due to the KSP constants. The thiosalts have KSP values which are a lot higher than the sulfide products. In addition to mercury, bismuth, copper, cadmium, as well as lead are not soluble in ammonium polysulfide because of their very low KSP values. Example would be cadmium, which has a KSP value of 8.0 times 10 to the minus 27. After decanting, adding hydrochloric acid to the filtrate reprecipitates the tin, antimony, and arsenic as sulfites. If these elements are not present, a white precipitate will form. The precipitate is discarded as this white precipitate is sulfur. After decanting the test tube with the filtrate, label as 2B, and the test tube labeled 2, relabeled as 2A. To separate the group 2 precipitate into groups 2A and 2B, wash the precipitate in test tube number 2 with cold distilled water to remove any soluble contaminants. Decant the filtrate and discard it. To the precipitate, add a few drops of ammonium polysulfate, equal to the volume of the precipitate. This should be a ratio of 1:1. Heat and stir in a water bath. Decant the filtrate into a clean test tube and label it as 2B. Relabel the test tube number 2 as 2A. To the filtrate, test tube 2B, add a few drops of hydrochloric acid. If a white precipitate forms, discard it as it will be sulfur. If the color of the precipitate is different in color, not white, it will be group 2B elements of tin, antimony, and arsenic. Then centrifuge and decant and discard the liquid, not the precipitate. The group 2A test tube will contain the rest of the analyte, being the copper, mercury, if any, cadmium, and the bismuth. I would like to focus on the precipitate that is contained in the group 2B test tube. There are a few reactions that take place that are important to observe. Adding hydrochloric acid to the precipitate dissolves the tin and the antimony. However, due to the very low KSP value of the arsenic complex, it remains as a residue with sulfur. It is not soluble. The first two are in regards to the tin and the antimony. Adding the hydrochloric acid creates a product known as hexachlorostenate acid, as well as antimony trichloride, which is SbCl3 as shown. Adding ammonium carbonate to the residue redissolves the arsenic, leaving the sulfur, which is separated and discarded. Hydrochloric acid is then added to the filtrate to precipitate the arsenic. The yellow precipitate confirms the presence of arsenic in the sample. The filtrate containing the tin and the antimony is divided into two separate subsamples. For the antimony, adding sodium hydroxide until basic, plus an excess of oxalic acid, then adding hydrogen sulfide gas while warming in a water bath precipitates the antimony. The orange precipitate that may form is the confirmation for the presence of antimony. For tin, the other subsample will still be acidic. Adding a piece of iron wire and removing after 5 minutes The adding of a couple of drops of mercury dichloride will form a white precipitate. This confirms the tin. To separate and confirm the presence of the group 2b elements of antimony, tin, and arsenic, wash the group 2 precipitate with cold distilled water to remove soluble contaminants, if any. Decant and discard the wash water. Add 5 drops of hydrochloric acid to the residue and decant that into a clean test tube. Set the liquid portion aside and do not discard. To the precipitate, add 5 drops of ammonium carbonate and bring it to a boil over a Bunsen burner, but do not boil it dry. If a precipitate forms, centrifuge and decant into a clean test tube and discard the precipitate. It will be unwanted sulfur. To the liquid portion, add some hydrochloric acid until it is acidic. Now, if a yellow precipitate forms, it confirms the presence of arsenic in your sample. To the remaining filtrate that was set aside after washing your group 2b precipitate with the distilled cold water, to that remaining filtrate, add an equal amount of distilled water to a ratio of 1:1. Then divide the filtrate into 2 equal subsamples. To subsample A, add some sodium hydroxide until it's just basic. Then add an excess amount of solid oxalic acid and warm it on a water bath. Place some hydrogen sulfide gas through the sample. If an orange precipitate forms, it confirms the presence of antimony in the original sample. To the subsample B, place a piece of iron wire into the solution and let it stand for 5 minutes. Then remove it. Add 2 drops to 3 drops of mercury dichloride solution to the filtrate. If a white precipitate forms, it'll confirm the presence of tin. Since we have separated the group 2 elements and showed the process of confirming the presence of any group 2b elements, I would like to focus on the group 2a reactions. By adding nitric acid to the precipitate, it will dissolve that precipitate. Boiling the filtrate may produce a precipitate. If so, it will be mercury sulfide. The precipitate will then be centrifuged and the filtrate decanted into a clean test tube. Okay. Combining potassium chlorate with hydrochloric acid produces a chlorine dioxide, potassium chloride, and water. The precipitate will dissolve when the 2 solutions are added. However, the potassium chloride will bond with the mercury to produce a mercury dichloride and sulfur. Adding stannous chloride produces mercury chloride, which precipitates as a white precipitate. Adding additional stannous chloride, the chlorine dissolves and the mercury reduces to elemental mercury, which gives the gray color. This gray color confirms the presence in the sample. The filtrate that we first decanted into the clean test tube will be acidic due to the nitric acid added. The lead, cadmium, bismuth, and copper were converted to nitrates. Using litmus paper, ammonium hydroxide is added until it is basic. The lead and the bismuth precipitates as hydroxides as shown. However, the copper and cadmium form a soluble ammonium nitrate complex and remains in solution. This effectively separates the 4 elements for further separation and confirmation. To the liquid that was retrained from the group 2 separation process, add some ammonium hydroxide to the filtrate until it's just basic. The pH value should be between 8 and 9. Any precipitate that forms is to be centrifuged and decanted into a clean test tube. Do not discard either the precipitate or the filtrate. Start with the liquid portion, that is, the filtrate. Take 2 drops of the liquid and place it into a clean test tube. Add some acetic acid until it's just acidic. If a brown precipitate appears, this confirms the presence of copper. The copper will mask the cadmium. If copper is present, add some potassium cyanide to the solution until the color disappears. Then pass some hydrogen sulfide gas through the solution. If a yellow precipitate forms, it confirms the presence of cadmium. The lead and the bismuth will still need to be separated from the retained precipitate that formed from the addition of the ammonium hydroxide. Wash the precipitate with distilled water, decant, and discard the wastewater as it may contain sulfur. To the residue, add 5 drops of 6 molar sodium hydroxide. Centrifuge and decant that into a clean test tube. To the liquid portion retained, add acetic acid until the solution is just acidic. The pH should be between 5 and 6. Then add a drop or 2 of potassium chromate solution. Now, if a yellow precipitate forms, it indicates the presence of lead. To the remaining precipitate, add 2 drops of sodium hydroxide and 1 drop of dilute stannous chloride. A black precipitate will confirm the presence of bismuth. Iron is a bit problematic and therefore must be determined. Iron 2, that is ferrous iron, is soluble, whereas iron 3 is not. The point is that in the iron group, ferric iron will only be precipitated. I left this issue to be addressed now, as there is another issue to be addressed in the next slide. But in reality, it should have been done before the separation process of the groups. As I mentioned in the group separation being part 3 of this series, I'd like to take 5 kilograms of sample, homogenize it, and quarter the sample, leaving some for future use. Out of the 2.5 kilos, a small amount is removed for iron determination. The process is as follows and is quite simple. 2 grams of sample is dissolved in hydrochloric acid. The reaction forms an aqueous iron chloride which has the formula FeCl2. It also forms iron chlorite, or FeCl3. Once the sample is dissolved, it is divided into 2 separate subsamples. To the first test tube, 1 drop of potassium ferrocyanide is added. If a blue-black precipitate forms, it confirms the presence of ferric iron. To the second test tube, add a drop of potassium hexacyanoferrate 3, commonly referred to as red prussiate. A black precipitate confirms the presence of ferrous iron. Both may be present in the sample. At this point in time, I'd like to talk about the cyanide problem. If you have viewed my series on fire assay for small miners, it was discussed to keep any cyanide solutions at a pH value well above 10. This prevents or suppresses the formation of that highly toxic and deadly hydrogen cyanide gas. However, as small-scale miners and prospectors, as well as some of you hobbyists out there, we tend to take samples from mine tailings every once in a while. Now, these samples may contain cyanide as a residue. The cyanide must be destroyed. This can be accomplished with ease, but must be done with safety in mind. Cyanide gas can be deadly. Before testing the sample, that is, separating it into groups, using a fume hood or being outside with the wind at your back, dissolve the sample in nitric acid while heating in a sand or water bath. Do not discard the residual. Then gently evaporate until dryness, after which continue with the group separation. However, starting with the hydrochloric acid for group 1, let the sample digest for about an hour before centrifuging and decanting, as I've shown in part 3 of this series, group separation. At this point in time, I need to take a step backwards and talk about some of the common interferences. During the group 2 separation that was discussed in part 3, and I forgot to mention, any phosphate present in the ore sample may result in a loss of analyte. Elements such as magnesium, calcium, barium, strontium, zinc, as well as manganese, will precipitate out as phosphates, along with the hydroxides. Therefore, their removal is necessary and should be completed after the group 2 separation and before the group 3 procedure. This is carried out by boiling the group 3 solution, but do not boil it dry. Then add an equal amount of bromine water and boil to remove excess bromine. The solution is then made acidic by adding 2 drops of nitric acid along with 6 drops of 5% zirconium nitrate. The solution is warmed to almost boiling and then centrifuged. If a precipitate forms, centrifuge but do not separate. Add another drop of zirconium nitrate and repeat process until all precipitate stops forming. Then centrifuge and decant. Discard the precipitate. It will be zirconium phosphate. The phosphate is thus eliminated in this manner. As for the borates and fluorides, they will combine with the group 4 and 5 elements. These complexes are insoluble, not soluble in ammonia solution. By repeated evaporation of the precipitate with hydrochloric acid will volatilize the borates and fluorides. It also eliminates the silica. Once removed, continue with the group 3 process. The iron and manganese will have to be separated. Keep in mind the only iron that may be present will be ferric iron or iron 3. Adding sodium peroxide to the precipitate forms a precipitate containing the ferric iron and the manganese. Both are not soluble as hydroxides in a peroxide solution. The aluminum and chromate will form a soluble metallic complex with the sodium, as well as a soluble aluminum oxide complex. Adding acetic acid to the solution combines with the aluminum oxide, forming aluminum acetate. Adding ammonium carbonate precipitates a red-colored precipitate confirming the presence of aluminum in the sample. The addition of the sodium peroxide formed an aqueous sodium chromate. Adding lead acetate to the solution allows for the formation of a yellow-colored lead chromate precipitate. Since chromate contains the chromium element, it confirms the presence of chromium in the sample. By dissolving the precipitate that was generated by the addition of the sodium peroxide in a hydrochloric acid, produced iron 3 chloride. Adding the potassium cyanide produces a blue-black precipitate. This precipitate is the formation of ferric iron, if it was present in the sample. The precipitate may also contain some manganese, in the form of manganese oxide. The sodium peroxide combines to form a sodium manganese oxide complex. The addition of nitric acid forms an aqueous manganese oxide compound, causing the filtrate to turn red in color. This red filtrate confirms the manganese in the sample. After the removal of the borates, etc., and labeling that test tube number 3, which is your group 3 test tube, wash the precipitate with distilled water and decant. The wash water can be discarded. Bulk up that residue with 10 drops of distilled water and stir to coagulate. Then add a small amount of sodium peroxide and boil it until the effervescence ceases. Centrifuge and decant into a clean test tube. Divide the precipitate in half. The first half dissolve in dilute hydrochloric acid. Once dissolved, add 1 drop of potassium ferrocyanide. A blue-black precipitate may form. This will confirm the presence of ferric iron in the ore sample. To the other half of the precipitate, add 2 drops of nitric acid, 4 drops of distilled water, and a trace amount of solid sodium bismuthate. Stir the precipitate while warming in a water bath. Then allow the residue to settle. If the liquid portion turns red in color, it'll confirm the presence of manganese. The liquid portion that was decanted after the addition of the sodium peroxide, divide this solution in half. To the first half, add some acetic acid until it's just acidic. Then add 1 drop of lead acetate. If a yellow precipitate forms, it'll confirm the presence of chromium. To the other half of the filtrate, add 1 drop of acetic acid, along with 1 drop of 0.1% aluminium. Then add an excess amount of ammonium carbonate solution. If a red precipitate forms, it'll confirm the presence of aluminum. The precipitate in the number 4 test tube consists of the group 4 elements. For confirmation, these elements need to be separated. To the test tube, ammonium hydroxide is added. Sulfides do not dissolve easily in hydroxide solutions. The sulfide, as shown, will break down to form hydroxides. The ammonium sulfate will also break down, leaving elemental sulfur which recombines with the metal, resulting back to its original form. The reaction shown is not expanded to show the full reaction, but it does show it by the use of the double arrow. Since the sulfide compounds do not change their state, adding hydrochloric acid will result in a chloride molecule and hydrogen sulfide gas will be formed. However, the nickel and the cobalt molecules will slightly be solubilized due to their lower KSP values and will remain mostly unreacted, leaving them in their original form as sulfides. Adding additional hydrochloric acid and some potassium chlorite to the precipitate will result in elemental chlorides of cobalt and nickel. The water is boiled to remove the sulfur. The solution is then divided into 2 portions, and to the first portion, an indicator being dimethylglyoxime is added. Ammonium hydroxide is added drop by drop until the solution is just basic. A scarlet precipitate will confirm the presence of the nickel. The cobalt in the water is unstable, but can be dissolved in an ether and separated using a gravimetric separation technique. The ether will mix with amyl alcohol, but this solution will not mix with the water. It will float on top due to the difference in densities. The cobalt iron will turn the solution blue, confirming the cobalt. For the zinc, the liquid portion is boiled to remove the sulfur as hydrogen sulfide gas. Sodium hydroxide is added to make the solution basic. It also forms a sodium-zinc oxide complex which is soluble. Passing hydrogen sulfide gas through the solution eliminates some of the free sulfur, which is soluble in a sodium solution. Potassium ferrocyanide is added, which combines with the zinc to form a non-soluble zinc ferrocyanide precipitate. This white-colored precipitate confirms the presence of the zinc. To the other precipitate, adding 2 drops of concentrated nitric acid, 4 drops of water to bulk it up, and a trace of sodium bismuthate, sorry for the pronunciation, as an indicator. This will dissolve the manganese as a nitrate. A red-colored filtrate will confirm the presence of manganese. To separate and confirm the group 4 elements, to the labeled number 4 test tube, add an equal amount of distilled water and 1 or 2 drops of ammonium hydroxide. Stir, decant, and discard the wash water. Add a few drops of diluted hydrochloric acid and stir. Centrifuge and decant into a clean test tube. Cap the residue and label as 4A. Now boil the liquid portion to remove the free sulfur, but do not boil it dry. Add sodium hydroxide solution until it's just basic. Centrifuge and decant this into a clean test tube. Cap the residual and label as 4B. To this liquid portion, pass some hydrogen sulfide gas through the solution. Centrifuge and discard the wastewater. Add some hydrochloric acid to dissolve the precipitate, then add 1 drop of potassium ferrocyanide. A white precipitate that may form confirms the presence of zinc in the sample. To the precipitate labeled 4B, add 2 drops of concentrated nitric acid, 4 drops of distilled water to bulk it up, and a trace amount of sodium bismuthate as an indicator. If the liquid turns red, it confirms the presence of manganese. To the residue in test tube 4A, add 3 drops of concentrated hydrochloric acid, 3 drops of potassium chlorate. Boil the solution till all the fuming ceases, then bulk up with an equal amount of distilled water. Separate the solution into 2 equal parts. To the first part, add 3 crystals of potassium thiocyanate, 6 drops of amyl alcohol, 5 drops of ether, and shake the test tube to thoroughly mix the solution. Allow this to settle. The solution should separate into 2 separate layers. If the top layer turns blue, it confirms the presence of cobalt. To the other half of the solution, add 1 drop of dimethylglyoxime and 50% ammonium hydroxide dropwise until it's just basic. Any scarlet-colored precipitate that forms will confirm the presence of nickel. To the carbonate precipitate in the test tube labeled number 5, acetic acid is added. This forms acetates of calcium, barium, and strontium. When potassium chromate is added, a precipitate of barium chromate may result. From this precipitate, a small portion is burned in a Bunsen burner flame. The observation of an apple green flame confirms the barium. To the remaining filtrate, the addition of ammonium sulfate may produce a strontium sulfate precipitate. When a small portion of this precipitate is burned in the Bunsen burner flame, if a crimson-colored flame is observed, it confirms the presence of strontium. The calcium may also be confirmed by a flame test. However, it is not reliable as the flame becomes intermittent. The calcium acetate is soluble in ammonium sulfate solution, as it complexes into calcium ammonium sulfate. The addition of ammonium oxalate to the solution may produce a calcium oxalate precipitate. A white precipitate confirms the presence of calcium. To the test tube labeled number 5, add a few drops of distilled water. Decant and discard the water. Then add 10 drops of acetic acid and boil to remove the carbon dioxide. Then add potassium chromate, drop per drop until precipitate ceases. Centrifuge and decant into a clean test tube. Take a small piece of precipitate using a stainless steel wire scoop and burn it in a Bunsen burner flame. If the result observed is an apple green flame, it confirms the presence of barium in the sample. Now to the filtrate, that is the liquid portion, add a few drops of ammonium hydroxide. Then add an excess amount of solid ammonium sulfate. Then boil the liquid. Centrifuge and decant any precipitate that is formed. Take a small piece of precipitate using a clean stainless steel wire scoop and burn it in the Bunsen burner flame. If the result observed is a crimson-colored flame, it confirms the presence of strontium. To the filtrate, add 1 drop of ammonium oxalate solution. If a white precipitate forms, it confirms the presence of calcium. Mixing magnesium acetate with uranyl acetate forms a soluble magnesium uranyl acetate. When reactive with the sodium ions, an insoluble sodium magnesium uranyl acetate, if formed, will precipitate. A yellow crystal precipitate that forms does indicate the presence of sodium. For the potassium, adding perchloric acid produces a potassium chlorate, which is not soluble. It presents itself as a white precipitate. There is a second test to confirm. Adding cobalt nitrate reacts with the potassium to form a cobalt precipitate, which confirms the presence of potassium in the sample. For the manganese, a spot test is conducted. There are two tests used to confirm the presence of manganese. The first test uses Titan yellow as an indicator. It is introduced before the addition of a hydroxide. Sodium hydroxide is used as the reactant. Between pH 12 and 13, it will change color from yellow to red. The red color confirms the presence of manganese. To further confirm the results, magneson reagent, sometimes referred to as azoviolet, is added prior to the hydroxide. Below pH 11 it will be yellow. Above pH 13 it will turn violet, which does confirm the presence of manganese in the sample. A word of caution here. Uranyl acetate is formed from depleted uranium. It is toxic and targets the liver and your kidneys. Do not inhale or ingest. That is, digest. Use appropriate personal protective equipment when handling magnesium uranyl acetate. The test tube that was labeled number 6 during the group separation should contain only a solution containing the rest of the soluble analytes. These analytes will need to be brought back into a solid residue. The solution will still contain ammonium salts, which will need to be removed. This is completed by volatilizing the ammonium salts. The solution is then transferred to a nickel crucible and gently heated to evaporate to dryness. The residue is then moistened with concentrated nitric acid and heated to a red heat and then cooled. This is achieved by placing the crucible over a Bunsen burner. Once cooled, the residue is ground or pulverized to a fine powder and transferred to a test tube. 5 drops of acetic acid is then added to dissolve the residue along with 5 drops of distilled water. It is then divided into 3 equal portions. From the first portion, 2 drops of the solution, using a pipette or an eyedropper, is placed into a test tube. 2 drops of sodium magnesium uranyl acetate is added, along with 3 drops of alcohol. If a yellow crystalline precipitate forms, it confirms the presence of sodium. From the second portion, 1 drop of the solution is placed on a watch glass. A glass plate will also suffice. 2 drops of perchloric acid is then added. If a white precipitate forms, it may confirm the presence of potassium. Another drop of the same solution is placed on another watch glass, and 1 drop of sodium cobalt nitrate is added. A yellow precipitate will confirm the presence of potassium. From the third portion of solution, 1 drop is placed on a watch glass, and 1 drop of Titan yellow is added as an indicator. 2 drops of diluted sodium hydroxide are then added. The formation of a red precipitate may confirm the presence of magnesium. On another watch glass, another drop of solution is placed. 1 drop of magneson reagent is added, along with 2 drops of the diluted sodium hydroxide. A blue precipitate will confirm the presence of the magnesium in the sample. This short video demonstrates a simple method to qualitatively determine the unknown analytes that may be in your ore samples. The Physics Teacher's YouTube channel is an excellent source for those that may be interested in chemistry. I added this as a primer for the next part 5 in this series. If you liked this video, check out his YouTube channel. Like and subscribe. I know that he would appreciate it.
Welcome to Physics Teacher. In this video, we're going to look at how you can determine the presence of certain ions in a solution qualitatively. One way is to use a double displacement reaction and look for a precipitate. Let's go over an example. Say we have an unknown solution and we want to determine if either lead or strontium ions are present in this solution. What we can do is mix it with a solution that we know will react to form a precipitate with either of these ions. To determine which solution to use in our test, we need to look at the solubility table. First, let's look at where lead and strontium have a low solubility. There are many options, but let's keep it simple. Chlorine and sulfate work nicely. Since sulfate has a low solubility with both lead and strontium, let's use chlorine to first test for lead. So, what can we combine with chlorine then to make a solution? We need something with high solubility. Keeping it simple, using alkali or group 1 metals work best. Let's use sodium chloride. When we look at the double displacement reaction with unknown solution AB and known solution sodium chloride, the metal A combines with chlorine, and sodium combines with the nonmetal B. Since sodium is from group 1, it doesn't matter what B is, as it will be highly soluble. However, if A is lead, then lead 2 chloride is formed, which has low solubility and precipitates. Therefore, if we see that precipitate, we can confirm the presence of lead. If we don't, no lead. Now, if there is a precipitate, filter it out of our solution and let's move on to test for strontium. Once again, what solution should we add to test for strontium ions? We need a compound that will dissolve in water, but when it undergoes a double displacement reaction, will precipitate if strontium is present. Now, since we have determined whether or not lead is present, we can use sulfate to determine if strontium is present. Once again, keep it simple. Sodium sulfate is highly soluble and will work as our known solution. If strontium is present, strontium sulfate is formed in the reaction and precipitates due to its low solubility. If not, then no precipitate will form. And that is how we can qualitatively test for ions in ionic compounds. Be sure to subscribe if you like this video so you don't miss the next one.
Most small miners, homegrown prospectors like myself and hobbyists, we have the tendency to miss the boat. That is, not testing for valuable industrial minerals in their small operations. Most of us concentrate our efforts to find that elusive precious metals such as gold, platinum, silver, etc. However, copper, lead, lithium, barium, cobalt, and more just might be your gravy boat. Industrial metals make up the lifeline of our economy and our comfortable way of life. Many miners are mostly placer miners, and most are throwing these minerals away as tailings. What they may be throwing away is a potential for a more profitable opportunity. Knowing what you have may be worth more than the gold or silver, especially if your ventures start to pan dry. In part 3 of this series, I tried to explain the process and procedure of chemically separating your samples into groups of analytes. In this part 4, I have discussed the reactions, process, and procedure for the separation and the determination of the analyte in each group. Qualitative chemical analysis is a simple but time-consuming effort, but worth it. By conducting such an analysis, you can identify what you have. Knowing what you have can determine if you need to send some samples to a lab for further analysis or statistical evaluation. These 4 parts in the series are the starting point for what is referred to as quantitative chemical analysis. I know this presentation was lengthy, and I hope that one may have benefited from these 4 parts of this series. I hope that you would like and share. Just pass this on to anyone who may benefit from these presentations. I hope to have part 5 completed soon. I'm Rob Boyko, Boyko Mineral Exploration, and I thank you for watching.